To familiarize ourselves with the different number sets is our target for this mathematics video. Let's start with a set of numbers known as whole numbers. Whole numbers are simply the numbers 0, 1, 2, 3, 4, 5, and so on. No fractions are included, except the fractions which were simplified into whole numbers because the denominator is 1, like 4 over 1, or it's simply 4. Or the denominator is a multiple of the numerator, like 6 over 3, or it's 2. Here, for example, 0, 1, 2, 48, 99, 5,000, all are whole numbers. But numbers like 1/2 or 5/10, 2/3, 1 2/10, 1 75/100, 1 over 1000, 97 over 32, they are not whole numbers. They have other type of number set. Whole numbers, but without the 0, or without considering 0, are what we call counting numbers. 0 is not included because we cannot count 0. So counting numbers are 1, 2, 3, 4, 5, and so on. Counting numbers are also known as natural numbers. However, in some fields of mathematics, natural numbers are whole numbers from 0 upwards, not just from 1 upwards. Next set of numbers is known as integers. Whole numbers are a subset of integers. Subset or part of integers. Integers are like whole numbers, but they also include negative numbers like negative 99, negative 5, negative 1300. So integers can be negative, as in negative 1, negative 2, negative 3, negative 4, and so on. Integers can be positive, as in for 1, 2, 3, 4, and so on, or 0. So we can put that all together like this. One half two-thirds, 97 over 32 are not integers. The numbers that you can make by dividing one integer by another, but not dividing by 0, in other words, fractions, are also known as rational numbers. 1/2 or 5/10, which is described as terminating, as an example of rational numbers. 2/3 or 6/10, where 6 is with bar that indicates 6 is being repeated infinitely, is a non-terminating but repeating number, a rational number. And 97 over 32, 1 2800, 1 over 1000, and many more are examples of rational numbers, together with all integers, because all integers have fractional equivalent, like example negative 5. In fraction, negative 5 over 1, 2. In fraction, 2 over 1, 0, 0 over 1, negative 1300, or negative 1300 over 1. However, some numbers cannot be written as a simple fraction or a ratio of two integers. They are called irrational numbers. Pi. Pi is a very known irrational number. People have calculated pi to over a quadrillion decimal places, and still there is no pattern. The first few digits look like this. The number e, or ruler number, is another famous irrational number. People have also calculated Euler number to lots of decimal places without any pattern showing. The first few digits look like this. Another irrational number is the golden ratio. The first few digits look like this. A non-terminating and non-repeating number. Many square roots, cube roots, etc. are also irrational numbers. Examples are square root of 2. When transformed to decimal, is a non-terminating number. Negative square root of 5 also is a non-terminating and non-repeating number. Cube root of 26 is an irrational number, but square root of 5, which is equal to 2, square root of 9, which is equal to 3, they are rational. So take note, not all roots are irrational. All rational and irrational make up real numbers. A simple way to think about the real numbers is that real number is any point anywhere on the number line, not just the whole numbers. They are called real numbers because they are not imaginary numbers. So another set of numbers is the imaginary numbers. Imaginary numbers are numbers that when squared give a negative result. If you square a real number, you always get a positive or zero result. For example, 2 times 2 equals 4. And negative 2 times negative 2 equals still positive 4. It seems like we cannot multiply a number by itself to get a negative answer. But imagine that there is such a number, call it I for imaginary, that could do this. I for imaginary, which is a value of square root of negative 1. We could do by multiplying I by itself equals a negative number, a negative number 1. Would it be useful, and how could we do it? Well, by taking the square root of both sides, we get this. I is equal to square root of negative 1, which means that I is the answer to the square root of negative 1. So imaginary numbers can seem impossible, but they are still useful, very useful, because by simply accepting that I or imaginary exists, we can solve things that need the square root of a negative number. 5i is another example of imaginary number. Euler times I and pi times I also are imaginary numbers. Together with I, they are classified as pure imaginary numbers. We can have imaginary numbers like 5 plus 9i, 1 plus I, pi plus 2i, Euler number plus pi I. These imaginary numbers have real and imaginary parts, and the reason should be I for imaginary number. Most numbers are used every day, and these most numbers we use every day are algebraic numbers, but some or not, such as pi and Euler number. Pi and Euler numbers are examples of transcendental numbers. Transcendental numbers is any number that is not an algebraic number. Now, what are algebraic numbers? To be algebraic, a number must be the root of a non-zero polynomial equation with rational coefficients. Here are some algebraic equations and the number set needed to solve them. Like equation x minus 3 equals 0, the solution is 3, a natural number. X plus 7 equals 0, the solution is negative 7, an integer. For x minus 1 equals 0, 1/4 is the solution, not a rational number. X squared minus x minus 1 equals 0, the solution is a golden ratio, or the value for x could also be as an estimated value of 62/100, irrational numbers. X squared minus 2 equals 0. The solution is that x is equal to positive negative square root of 2. Real numbers, and x squared plus 1 equals 0. The solution is positive negative square root of negative 1. Imaginary numbers, complex numbers. It seems like every number is algebraic. All integers are algebraic, and all rational numbers are algebraic, and square root of 2 is algebraic, and the imaginary number I is algebraic, so it's golden ratio, algebraic. We can notice that real numbers include the algebraic numbers and transcendental numbers. However, rational and imaginary may or may not be algebraic numbers. Like irrational numbers, pi, Euler, golden ratio. Only golden ratio among the three is an algebraic number. Also, with the imaginary numbers, there are portions of imaginary numbers that are considered algebraic numbers and some are not. Now, combinations of real and imaginary numbers make up the complex numbers. Really, any real or imaginary number can be in the form of a plus bi, where a and b are real and I as imaginary. The values of a and b can be 0, so the set of real numbers and the set of imaginary numbers are subsets or parts of the set of complex numbers. Just like this, 1 plus I, 5 plus 9i, even negative 7 and 2 times I, pi I. They are imaginary and complex, because it confirms with the form a plus bi, where a and b are real and I imaginary. Another example in the form of a plus bi is 4 plus 0i. When simplified, is simply 4. So 4 is a real and complex number. Using the diagram, take note: natural numbers or counting numbers and whole numbers are a subset of integers. Integers are a subset of rational numbers. Rational numbers are a subset of real numbers. Real numbers include algebraic and transcendental numbers. Algebraic numbers may or may not include irrational and imaginary numbers. Combinations of real and imaginary numbers make up the complex numbers. Now, try this. Are you not familiar with the different number sets? You can complete this diagram.